Hello everyone, this is Professor Kuehn. Today we'll be talking about Chapter 3 from A Student's Guide to the Great Physics texts. This is from Galileo's Dialogues concerning two new sciences. The specific chapter we're discussing today is on Archimedes' principle and its relationship to the speed of falling bodies. Just by way of review, you might recall that in the previous chapter, Salviati and Segredo in Simplicio were discussing the structure of matter. Specifically, Salviati was claiming that the expansion and the contraction of substances when you heat them or cool them, for example, can be readily explained if one admits that they contain many or perhaps even an infinite number of tiny vacua. This was on page 30 of the book. So the rule of thumb, however, is that nature does not allow for a vacuum. This was the idea that they had inherited from ancient and earlier medieval thinkers. So if nature does not allow a vacuum, then of course it can't allow an infinite number of them. This would really fly in the face of the common knowledge at the time. So what we see at the beginning of this chapter 3 is Salviati and Segredo and Simplicio reviewing for themselves why it is that they have this idea that nature abhors a vacuum or doesn't allow a vacuum. And some of the reasons that one might have for holding to this, there's perhaps three reasons. The first is that it is really never empirically observed. That is, you never actually see a vacuum, right? So when you even nowadays, when you turn on a vacuum cleaner or pump gas out of a chamber, there's always a little bit of air left behind. One cannot even today make a perfect vacuum. And especially back at this time, Otto von Guericke was in the process of developing his experiments to try to create a vacuum, but it's a very contentious issue whether or not a vacuum can exist in nature, and especially in light of the fact that no one had been able to create one up until this point that they were aware of. So it's not something that's empirically observable. The second reason why one might reject a vacuum is because it can lead to logical absurdities. So to give you a sense of how this argument goes, there was around this time a philosopher named René Descartes. He was a little bit before and during Galileo. And Descartes argued against the existence of a vacuum in the following way. He said, when talking to people who believed in a vacuum, he would ask them, okay, so if outer space is a vacuum, which is what you claim, right? And they would say yes. He said, okay, so what is between the Earth and the sun? Well, a vacuum, they would say. Well, because space is a vacuum after all. Well, if what's between the Earth and sun is a vacuum, then, and vacuum means nothing, that's the definition of a vacuum after all, then that means there's nothing separating the Earth and the sun, right? And they would say, well, and he said, well, that means they're touching, right? If there's nothing separating the Earth and the sun, they said, no, that's what I mean. There is a vacuum separating them, but a vacuum, he would say, is nothing. So it leads to this kind of logical absurdity that if you mean nothing by a vacuum, it seems to imply that spatially separated objects are in fact touching. So this gets to the root of what we actually mean by a vacuum and whether one can create one. So that would be the second reason why someone might reject the existence of a vacuum. A third reason is, and this dates back to the time of Aristotle, and I think I went through this a little bit earlier in the semester, but maybe it's worth saying it again, is that it would seem to imply instantaneous motion if there was a such thing as a vacuum. That is, it would imply teleportation. Why, one might ask, does the existence of a vacuum imply instantaneous motion? Well, let me just write this down just for to make this a little more clear. So here's the question. Why might the existence of a vacuum, or the creation of a vacuum, the existence of a vacuum, imply instantaneous motion? You might call this teleportation or infinite velocity. And the answer, and this is the answer that Aristotle gave, and this is why Aristotle, for example, one of the reasons why he rejected the existence of vacuum, it had to do with his theory of falling bodies. He said that for falling bodies, or for falling objects, the speed or the velocity that they achieve is proportional to the weight of the object. So if you double the weight of an object, you double the speed, and so on. And so that's the first point. And the more relevant one, the second point, is that the speed of a falling object is proportional to 1 over the density, that's a Greek letter rho for the density of the medium through which they're falling. And notice here that if you believe that the speed of an object is inversely proportional to the density, which seems like a kind of common sense idea, right? So when something's falling in air, it falls very quickly. When it's falling through water, which has a higher density, the speed is slower. So there's some common sense behind this. But if, notice that the density goes to 0 as it would in a vacuum, you would arrive at an infinite velocity. So this would imply, that is, if the density approaches 0, that the velocity of the falling object would approach infinity, because 1 over 0 is infinity. And that implies instantaneous motion or teleportation. But instantaneous motion, velocity equals infinity, is absurd or ridiculous, said Aristotle. And so since this cannot happen, that means this cannot happen, which means there's no such thing as a vacuum. You might for a moment think about what, if you were going to reject this argument, how would you attack it. So what are the weak points in this argument? You might think about that on your own, because I suspect that you may believe in vacuum, and you may also believe that the density of a medium affects the speed of the falling object. So how would you attack this kind of argument? So I'll leave that to your own time to think about that. Now, so these are the reasons. I've just kind of summarized the reasons. This one I gave right here is the last of the 3 reasons I mentioned, but I've summarized some reasons why people did not believe in a vacuum. So what happens next in the dialogues is that Salviati critiques Aristotle's theory of falling objects, theory of falling bodies. Because after all, Salviati is going to, on behalf of Galileo, he is going to argue that there are vacua. That's what he's trying to demonstrate. And in order to argue there are vacua, he has to deal with these kinds of arguments that Aristotle is presenting here. So first of all, let's look at some of the counter arguments, some of the critiques or counter arguments of the Aristotelian theory of falling bodies. So first of all, this is something Salviati points out. He says, even if motion in a vacuum was impossible, this doesn't necessarily mean that you can't have a vacuum at all. Okay, so even if motion in a vacuum is absurd because of the arguments that Aristotle gives right here, that does not imply, oops, my computer's frozen up here. Pause for a minute. That does not imply that a vacuum is impossible. All that it would imply is that motion in a vacuum is impossible, right? So it doesn't necessarily imply that a vacuum itself is impossible, okay? So that's one way that Salviati critiques this argument of Aristotle's. A second critique, and this is right around page, so this was around page 31. The second one, which is around page 32, is that Aristotle probably didn't even test this theory. Aristotle probably did not test, at least carefully, his assertions about falling bodies. So Galileo here is using an empirical or experimental critique. He's saying if you actually carry out an experiment, you'll find that the speed of an object is not actually proportional to the weight of the object, and it's not proportional to the inverse of the density of the medium. How do we know that? Well, he says if you go ahead and drop an object from a height, and let's say you drop, so if you drop a 1 pound weight and a 200 pound weight, so think about two little small lead ball and a big lead ball, and you let them both fall from the same height, it is true that this one may hit the ground just a tiny bit earlier than this one. But according to this theory, it would imply that this one would travel at 200 times the speed and get there much faster than the light one. And although they don't hit at exactly the same time, Galileo argues that his theory is going to be closer to the truth, that is closer to the observed results, than Aristotle's. Okay, so this suggests that at least the idea that the velocity is proportional to the weight is not correct. Okay, so that's one of the other arguments he gives. Okay, let me present one last argument against the Aristotelian theory of falling bodies, and I think I can probably squeeze this in over here. Okay, he says, let's continue to think about this velocity is proportional to weight argument. Okay, so he says, suppose now that you have two objects. Let's say you have a 4 pound weight, and you drop this, and it falls with some speed, the speed of the 4 pound weight, and then you also drop an 8 pound weight. And it, according to, let's take this seriously for the moment, the velocity of the 8 pound weight is going to be larger than the velocity of the 4 pound weight, right? So this one is going to be fast if we take Aristotle's theory seriously, and this one is going to be slower, right? He says, okay, now what about this? Let's suppose that we take these two weights, the 4 pound weight and the 8 pound weight, and you tie them together, or you attach them with some kind of string or a wire or something, okay? What would happen if you do this? Well, usually when you have two objects that are in motion and one's moving slower than the other one by itself, the slow one is going to kind of slow down the bigger one. It's going to exert a little bit of drag on it. It's like if you're running along with your little brother or little sister and they're slow and you're fast and you're trying to hold their hand, they are going to slow down your run. So you're going to fall slower than you would have originally. So in other words, they're both going to fall, but the speed is going to be, so the small object slows down the large one. This seems to be an implication of this theory, right? Good so far? All right, now wait a minute, but also think about it this way. If you take that 4-pound weight and that same 8-pound weight, and once again you tie them together, if you think about this thing as a whole, the composite object is in fact a 12-pound weight. And a 12-pound weight falls faster, according to Aristotle's theory, than either an 8-pound weight or a 4-pound weight. So this should fall very fast, right? Because a 12-pound weight falls very fast, faster than either one independently. So it seems like we have ambiguous results. In case A that we just considered, it seems that this composite object should fall slower than the 8-pound weight. And in case B, thinking about it this way, it implies that that composite object should fall faster than the 8-pound weight. So the question is, which is it? It seems like Aristotle's theory of falling bodies implies ambiguous results. And when a theory predicts ambiguous results, that is a not obvious answer, or rather two answers that contradict each other, there's probably something wrong with the theory. And this is precisely what Galileo points out. He says, if we take Aristotle's theory that the velocity is proportional to weight seriously, we run into these kinds of problems. So there must be a better theory of falling bodies than this one. And I'll stop there and continue this discussion next time.